Jeff is Director of Solutions and Technology at Infinera. This is Jeff's third time presenting at NANOG, and it's a pleasure to have him speaking with us today. With that, let's welcome Jeff to the stage.
Thank you, Jen. And thank you, everyone, for choosing this session. I last presented at NANOG 85 in Montreal, and that was on optical fiber capacity. So this time, Steve at the program committee, he said, would you like to present again? And I said, well, not much has changed in terms of optical fiber capacity. Should I choose another topic? So he said, oh yeah, let's think of something else. And we came up with AI as a topic. Now, given the fact that my day job is in optical transmission for submarine cables, you are probably going to witness a really good example of the Dunning-Kruger effect, right? So I hope I won't let you down, but this is a topic I've become quite passionate about, really, is AI, and it's everything but the network aspects of AI. So basically, we could start by taking a look at the background to AI. It's a very big topic, and generally speaking, we say that it began in 1956, a meeting at Dartmouth College, and the original AI was something called symbolic AI. And symbolic AI relies on explicit rules by programmers. Some of you may have messed around with like expert systems trying to write code. It basically ends up as a whole bunch of if-then constructs in your code. It's been extensively used in computer vision, robotics. It's still a very useful technique. But the one that's getting all of us excited at the moment is machine learning, which is where the AI can essentially change its own code. And deep learning is an example of machine learning that uses artificial neural networks as the mechanism, as the tool for machine learning. And then deep learning essentially refers to a neural network with lots of hidden layers. So the more hidden layers you have in your neural network, the more sophisticated that network becomes. So then we've got a subset of that again, which is generative AI. And generative AI is enabled by these deep learning networks, and it's where the AI can create its own new content, images, text, graphics, and so on. Now, in some applications, you'll find that generative AI becomes a natural language front end to a symbolic AI tool or a good old scripting tool. And in fact, in a lot of network applications, that's exactly what you'd use generative AI to do. So just to give you a comparison between symbolic AI and generative AI in robotics, of course, these could be robots, screwed to the ground next to a production line. And these robots essentially operate with a constrained 3D space. So the programmer can actually work out exactly what happens when the robot moves through that 3D space and all the things that it should give it in terms of outcomes. Now, generative AI is where we have much more autonomous robots. So these robots are, they could go off and do their own thing. And the AI has to be able to deal with situations that the human programmer hasn't anticipated. So when did AI get so hot and why? I highly recommend this paper. It's written by somebody called L.M. Poe. I have no idea who this person is, tried to find out who they were. This feels very much like a sort of graduate project or a thesis. It's not really a PhD thing. But there is a link to the full article here, and it's a really good history of AI. It includes that particular timeline, and what I like about it is this particular moment in AI history, 2017, where a seminal paper written by Google researchers introduced a new deep learning architecture called the transformer. And the AI that you're probably using today, if you use it on a regular basis, is probably based on a transformer architecture. The previous hot technology in AI was called recurrent neural networks, and that was a breakthrough in its own time. It's actually still quite useful in certain circumstances, but it struggles with long-range dependencies. So if you give the AI a very, very long prompt, recurrent neural networks will struggle to maintain the context between different parts of that prompt. The big breakthrough with transformers was to use an attention mechanism that allows the AI to make those links across a very, very large prompt. Now, this is why chatbots suddenly became very usable, because natural language, like for example, verbs in different languages could be at the beginning of the sentence, the middle of the sentence, the end of the sentence. So natural language is often a big challenge for other kinds of AI. Now, the drawbacks of transformers, they require really large data sets, and they require a lot of training processing. This will become important later on as I develop some more ideas. They have something called a quadratic complexity. Now, those of you who work with networks, and of course we all do, you'll be aware in a fully mesh network of quadratic complexity, because as the more connections you get in a fully mesh network, it scales with a quadratic sort of limit. Now, what could succeed a transformer approach? Well, many researchers are looking at these alternatives. They're looking at recurrent neural networks again and seeing what they can do to change them. Also looking at attentionless transformers to try to avoid the quadratic complexity problem. And then there's something called Megalodon, which is an example of maybe a first challenger in the market. So how does generative AI actually work? And this is a really superficial explanation. I'm trying to sort of give you an idea of why some of the scalability issues crop up in AI. So a very high-level view, you create a machine learning model. It's based on a neural network, and you give it an enormous amounts of data to train this model. It also requires a lot of processing power. GPT-4 took 3 months to train on a network of 25,000 Nvidia A100 GPUs. Now, just to give you an idea, these cost anywhere between $8,000 and $20,000 a piece, depending on how much memory you have in that GPU. It also consumed 50 gigawatt hours of electricity, which is about the same as 4,000 US homes for a year. So after the training has finished, you've got to do some quality control. Now, bear in mind, I had to submit these slides before DeepReach, all that news was released. But basically, this is where DeepReach is making a few breakthroughs, because the fine-tuning mechanism that a lot of people used at this point is something called reinforcement learning from human feedback, RLHF. So what this is you give the AI a whole set of test questions that you already have the answers to. And the AI will answer them, and then a whole bunch of trained humans will evaluate how good those answers are, and will then tune the model based on that. Now, what DeepReach were able to do, instead of using RLHF, they used something called reinforcement learning through variable rewards, RLVR. And that takes the human out of the picture. You can allow the AI itself to evaluate its answers and essentially reward itself, and it's an unsupervised reinforcement learning. At that point, you decide how you're going to deploy it. You might want to prune for performance. You might want to prune for size, have a smaller model that will fit in a smaller edge processor, for example. But everything within that orange dotted line is essentially the training phase of AI. Once you've finished training, you move to the inference phase, where normally you would freeze the model, you decide how you're going to deploy it. Is it going to be deployed on an edge data center? Is it in a car? Is it in a robot? Is it in a phone? And then you start to use it. Now, inference normally would use a tiny fraction of the power of the training phase. And it should happen very quickly, whereas training takes months. Inference would happen quickly, because we're expecting an answer fairly quickly with the AI. So an example of some sizes of these models, ChatGPT, the generative pre-trained transformer, this will try to predict the next word in a conversation based on probabilities. And what you might, a classic phrase you might pass it is nanog 93 is being held. What would the next likely word be in that sequence? And training would tell it that these words have different probabilities of being the best next word in that sequence. And in seems to be a good candidate. However, ChatGPT doesn't always select the highest ranked word because it would be very robotic and very predictable in terms of its responses if it did that. It will sometimes randomize the result. And in fact, if you've ever used ChatGPT, there is a temperature setting. The higher the temperature, the more random the results, the more creative the answers start to become. So the model itself, it's a text model, let's say. It uses a large language model. How big? Well, the number of parameters has grown over time from the original GPT through to GPT-4 with 1.76 trillion parameters. The length of the prompt is also increasing. And remember, with a transformer architecture, that's really hard to do because as you increase the size of the prompt, the level of processing, this quadratic complexity, really starts to kick in very hard. So we still managed to increase the length of these prompts, and the Megalodon architecture that I mentioned earlier, that actually is all focused on allowing infinite length prompts. So it's removing this quadratic scaling problem and allowing infinite prompts. Now, when we talk about tokens here, a token, you think of it as a word, but tokens are actually a unit of measurement. It may be a word, or it may be that the word is broken down into syllables. It just depends. There's no obvious pattern to it. However, I can start to talk a little bit more about it. So let's talk about the examples of these data structures where the artificial neural network, you're going to ask it a question. So the input tokens are created from the prompt that you enter. Inside the neural network, and GPT-4 has 120 of these layers inside the network, the probabilities are stored as tensors in the hidden layers. And then the output tokens are generated, that's the answer, that's generated by the output layer. So each of the nodes is represented by a tensor. A tensor is an n-dimensional array, basically. And we have special names for some of these. So the original one-dimensional tensor is called a vector. Two-dimensional tensor is a matrix. And then we say, oh, let's forget giving it special names. We just call it 3D, 4D, 5D tensors. So in a text-based AI, like GPT-3, the phrase that I started to enter, nanog 93, that's how it's tokenized. It's not, nanog 93 is not a token, but the syllables kind of end up almost as tokens. I actually ran that through the OpenAI token generator, and so I can tell you those are the tokens in ChatGPT. So those are stored within an individual vector. The vectors are assembled into matrices as the conversation progresses. So that's how the tensors are built up. If you were using a graphic-based AI, an image-based AI, you would use a 3D tensor because two of the dimensions are taken up with the coordinates of the pixel, and then the third dimension would be the color value of the pixel. And you can imagine if you wanted to start working with video, you'd just add another dimension. You'd add a time dimension that would tell you which image is being displayed at the time. So the fact that these are tensors will become important later on. So how do we use these models? There's three different approaches generally. You could use them as standalone tools. That's a way that a lot of us started to become familiar with AI, with the ChatGPT user interface, the Gemini user interface, and so on. You could have tools that are integrated within an application. So a word processor that has AI built in, a spreadsheet that has AI built in. That's available today with Office 365, Google Workspace, and so on. You can have custom AI solutions, and these are very often specific to a particular industry or even an application within an industry. And these are examples of compound AI systems. So what's a compound AI system? Well, take a simple example. How many vacation days do I have? If I ask ChatGPT that particular question, it will say, oh, Jeff, you've got, actually, no, it will say, you've got 10 days. And I can almost guarantee that that's wrong. But AI doesn't like to say, I don't know, right? It really doesn't like to say, I don't know. It will just make stuff up. And so it says, you've got 10 days. But it doesn't know who I am. It doesn't have access to my company's time off database, so how would it even know? However, a compound AI system, we can give a generic large language model like Gemini, Claude. We can give it access to a special or proprietary database of knowledge. So you'd start with your generic AI. Now you say, I'm Jeff Bennett. How many vacation days do I have left? So the generic AI acts as a natural language front end to that question, sends the query to the time off database. Time off database replies, and it says, you have 15 vacation days remaining, Jeff. So that's very good news. That's an example of something called RAG, or Retrieval Augmented Generation. So it's a form of compound AI system because you've combined a natural language front end with the AI with a proprietary database of information. And I think of it like in Who Wants to Be a Millionaire, it's like phone a friend, right? So you're the generic AI system and you phone a friend because they're an expert on baseball, let's say, if you get a baseball question. Examples of custom AI, legal AI. There's loads of examples of this for natural speech search, document drafting, contractual advice is a big one today. And there are two very, very famous professional tools on the market at the moment from LexisNexis and Thomson Reuters. And those of you who may be aware of those companies, they both started off as news search companies. And they expanded out and they bought databases of case law. And these are proprietary databases of legal examples. However, they claim to be hallucination-free, but are they really? There was a study by Stanford University, I've put a link to it there, of these two systems. And basically they're saying, yeah, it's not bad, but they still hallucinate between 17% and 33% of the time. So what does hallucinating mean in the context of legal AI? It makes up case law. And judges apparently don't like that. So they often get quite upset. Another hallucination example for images. I actually generated this from an image AI, I won't say which one, and I said, show a group of wristwatches on display. All of them show the time as 12:03, and this is what it showed. Now, they look like wristwatches, but why did it get the time wrong? And the answer is because watches are usually photographed with the hands at 10 and 2, because it turns out that from an aesthetic basis, they look better that way. It means the hands are not blocking the logo of the watch, they're not blocking the date window, and it looks like a smile. So that's why watches are normally photographed at 10 and 2. So when the AI learns what a wristwatch looks like, it always sees the hands at 10 and 2. Now, custom AI examples in medicine are getting quite interesting because I think in contrast to the legal world, it's succeeding a lot more in medicine. There are examples of HIPAA-compliant medical scribes that reduce the documentation workload on medical professionals. Examples of AI diagnostic medicine. Some people here may be aware of a TV show called House MD. Hugh Laurie plays a doctor who's a genius at medical diagnosis. So imagine if every patient had access to a Gregory House. They didn't have to go to his particular hospital. They'd all have access to this genius who was a brilliant diagnostician. Robotic surgery. Now, robotic surgery has been around for a long time, but with humans on the end of the controls. And robotic surgery is really favored by surgeons, has very, very good outcomes because the incisions are smaller. There's less trauma to the patient. And so you get faster recovery times. Now, it can take 15 years to train a human surgeon. So we've already got the controls there, available to be removed and replaced by an AI interface. In terms of new drug development, earlier on it was mentioned the Nobel Prize in Chemistry in 2024 was all about the protein folding that Google pioneered. 90% of new drugs fail during development. If you could reduce that failure rate using AI, then you would massively change the economics of new drug development. And there's a study by Accenture here showing a potential for $150 billion a year saved in US healthcare. Now, what this means is you look at the hyperscalers for AI, and they are seeing a once-in-a-lifetime opportunity to make a ton of cash from AI. And they are just thinking, it doesn't matter how much money we throw at this in terms of investment, it will give us a return on investment. We cannot afford not to do this. But the key question is, how do they make their AI better? And you can think of that in two different ways. Think of it in absolute terms and in relative terms. In absolute terms, if your AI is focused at a particular industry and it's a regulated industry, it has to pass whatever standards that industry is setting. For medical AI, it has to be better than a human surgeon or a diagnostic consultant. Your legal AI has to stop making stuff up, right? Because it's not going to succeed if it makes stuff up. In relative terms, Google wants a better AI than Meta, Amazon, Microsoft, and all the different permutations of that. So the big four are investing a lot of money. All the forecasts on AI spending, they seem to go out of date almost as quickly as they're published because of a bigger investment that somebody is making. Why are they throwing so much at that? Well, until recently, you couldn't point to a return on investment. But when you look at the latest quarterly results from the big companies, Microsoft, Google, Meta, Amazon, and Oracle as well. Oracle is seen as like almost like a neutral AI provider. All of them are basically crediting AI for huge increases in their profits. And then we had Stargate, the announcement in January of initially $100 billion expanding up to $500 billion in AI investments for building massive data centers. So it's really about, why do you need such massive data centers? Now, there's a high-level direction for AI in terms of making it better. And you'll have heard these terms. There's artificial narrow intelligence, which is AI that can be as good as a human, but in one specific area, like diagnostic medicine, for example. Then you've got artificial general intelligence. That's AI that can be as good as the best human brains at any task that it's given. And then we have artificial superintelligence, where basically the AI is outperforming humans at any task. Now, in terms of a timeline, we're here, artificial narrow intelligence. It would be great for me to say, we know that artificial general intelligence will happen this year, next year. Actually, somebody has to define what AGI actually is first. How do we know that we've got there? But then Steve Altman at OpenAI says we're basically thousands of days away from artificial superintelligence. And that's a very short time frame, right? It could be 3, 4, 5 years, which is not very long. So how do we make the model better? Well, we've got this pre-trained model, and it's frozen. It doesn't learn anymore. And it makes mistakes, right? You get mistakes in image-based processing, in text-based processing. It makes hallucinations. Well, you could fine-tune the AI. We could use this RLHF. But what DeepSeek is doing, they're improving their model performance, actually, by using this automated reinforcement learning. Gives them much, much better performance for a given amount of processing. And then, if you want to make it specialized, retrieval augmented generation will do that. Imagine a customer chatbot, for example, that retains your customer history, so it knows every conversation it's ever had with you. You don't have to go through all that hassle of explaining that you've already called them 15 times and they haven't figured out your problem. In my company, we've licensed Microsoft Copilot, and basically it runs inside our firewall. It can look at our documentation on our products, and we can ask it questions about our products. But that's proprietary information. It's inside our firewall. You wouldn't want it in the general AI model. And that applies to a lot of different aspects, like the legal AI, where somebody's paid for a database, so they don't want all of that information in the general model. Another way we can think about it is, why don't we just unfreeze the model? And as it's running, as people are asking it questions, we just tell it whether we like the answer or not. Well, that's a kind of fine-tuning. That's actually reinforcement learning. The problem is, who's going to tell it what is a good answer or a bad answer? There is a famous example of an AI that was released in the wild, allowed to learn, and what it learned from humans, after about 3 or 4 days, it was giving very inappropriate answers to various questions. Now, that actually is called continual learning. And it's a goal for the next generation of AI, and to some extent, we're starting to see it in terms of reinforcement learning. But continual learning has some challenges. It really needs a lot of compute at the inference phase. And certainly for the initial round of deployments of AI, we weren't expecting that. We were kind of expecting inference to be a lot lower in terms of compute. And now everyone's saying, oh no, that data center's got to be 10 times more powerful out at the edge there. We also need a wide variety of new data. And if that data's available, why didn't we put it in the training data set, right? So if you don't have decent data, it will hallucinate. If you allow it to be trained by ordinary humans, it's going to start giving some very strange answers. And in fact, the AI guru, Jeff Hawkins, this is a very good book, actually, 1,000 Brains, highly recommend it. He doesn't believe that current artificial neural networks are capable of effective continual learning. So we could allow the model to think for longer during inference. This is called inference time compute. Now, I'm happy to say that when I submitted these slides, I said this is going to be a big deal in 2025. And a week later, DeepSeek, that's the big thing that they were doing, inference time compute. Let the AI think for longer about the answer. So there's a statistic that if you allow the AI to run for 15 times longer at inference, it's like having a model that's been trained for 10 times longer. And you think, well, hang on, that doesn't sound like a very good trade. But it is, because think about it. It's 15 times longer than what? If it was taking half a second to respond, and it now takes 7.5 seconds, that's like having a model that instead of training for 3 months, you trained it for 2.5 years. So that is a huge difference in terms of inference performance. And that's from a presentation by Noam Brown, who's with OpenAI. So the primary way that people have been making their models better, and this comes from another OpenAI paper, Scaling Laws for Neural Language Models, is to just work harder, make the data set larger, make the parameters larger. And when you scale them, what these graphs are showing is that errors go down. As the models get more bigger and more sophisticated, the errors go down. But unfortunately, by scaling those two on the right, you have to scale compute. And that also means more electrical power. So can we claim that AI training is power efficient? Well, the human brain takes about 20 watts. An Nvidia A100 takes 700 watts. And GPT-4, with its 1.8 trillion parameters, its 13 trillion token data set, took 3 months on 25,000 A100s. So 50 gigawatt hours, 4,000 US homes. That's about 234,000 times the energy used by one brain. So not exactly energy efficient, because let's face it, we are trying to simulate a human brain here. And depending on where you did that training, you could be putting more or less CO2 into the atmosphere. In Sweden, 8 grams of CO2 per kilowatt hour. In Germany, 368. Why? Well, Germany closed down its nuclear power stations, and it had to extend the life of coal-burning power stations to make up the difference. So that puts a lot of CO2 into the atmosphere, 46 times more CO2. So why are these AI implementations so inefficient? Well, many AI problems are examples of what are called sparse computations. Within that neural network, a lot of the values of the tensors are actually zero. And you are performing matrix multiplication on these tensors. What do you get when you multiply something by zero? Zero. But the problem is, you have to do the calculation anyway. So you're expending the energy, and you already know the answer. Now, the human brain has evolved a mechanism to deal with that, because we face a lot of sparse computation problems. And the classic example is in a dinner party where you're surrounded by conversations, but you can focus in on the person that you're talking with. You can ignore all of that stuff. Another reason, we heard it this morning, actually, the lady from Juniper speaking this morning about network architectures for AI, and basically how memory sizes, how the models overflow a given memory size, how you have to be able to move information across between GPUs. And these local memories are too small for the model. The data has to be distributed, and efficiency drops as your latency increases. Now, there are ways that people are trying to think about how to enhance this to deal with the sparse problem is the spiking neural network. And it turns out, because we're trying to mimic human brains, how does a human neuron actually work? Well, it doesn't fire continually. Artificial neural networks, as information goes through them, they just fire continually. But we don't. We wait for a certain amount of stimulus to build up before the neuron fires. That's called well, when you emulate that, it's called a spiking neural network. And neuromorphic processors, Intel has one that it's testing at the moment. They are ways that we could implement this. So we can create neural networks that closely mimic the human brain. And unfortunately, neither of these approaches is commercially viable yet, but we're sort of on the first rungs of the ladder of this. So what hardware do we actually use today for AI? Well, GPUs. And why are GPUs favored for AI processing? I have a couple of links in the presentation there to YouTube videos that I found very interesting. First of all, why are GPUs used, but also why Nvidia seems to have an AI monopoly. And spoiler alert, it's because of their CUDA language architecture. So anyway, a deep learning model will comprise a large number of tensors, and these are matrices that you're going to perform matrix multiplication, and it turns out that it responds very well to parallel processing. Multi-core processors work very well for parallel processing. Now, a modern CPU might have 8 very complex cores with lots of threads in each core, and a modern GPU will have thousands of more simple cores, but they're perfectly fine for doing this matrix multiplication. And Nvidia H100 has 14,592 CUDA cores. So that's one of the reasons why Nvidia has this massive market share for AI processing. But it may not be that simple. Google, for example, has developed a tensor processing unit. And the logical argument is, well, when you look at GPUs, they just happen to be better at AI processing because they're highly parallel processing chips. But they also contain a lot of baggage because they used to be graphics processors. So you get all of this stuff that's on the chip that you probably don't need. So if you invented or if you designed a chip from scratch for AI, you could probably make it a lot more efficient. But it's not that simple either. GPUs may be better for fully connected neural networks. And these are good for general purpose AI. They don't scale as well. CPUs may be better for natural language processing for recurrent neural networks, and TPUs may be better for training convolutional neural networks that are very good for facial recognition. So you can imagine that these different applications may require different approaches. And also, you could ask the question, well, hang on, well, is the best engine for training also the best engine for inference? Because if I spend lots of money and build a training data center, can I not use that for inference? Well, there are 2 points of view. Today's training engine is tomorrow's inference engine. You will read that on Nvidia marketing material, for example. Or, option 2, infrastructure has to be purpose-built in order to be efficient, and these 2 phases of the process don't share a common purpose. And you can take your pick on which you prefer. This is an incomplete list of companies developing AI chips, and they all think they can do better than Nvidia, and they probably can in certain circumstances. If you watch the video that I put a link to, that guy will explain why he thinks there's this sort of barrier to entry because of the CUDA language architecture. Now, what about inference? So a training data center, each one of those little blocks in there is supposed to be a server rack, and obviously they're way, way bigger than I can draw on a slide. But these training data centers need tens or hundreds of thousands of GPUs running for months to train a model. But when you deploy, your deployment options for inference could include a large model that also needs quite a big data center to respond to thousands of users. It could also be a large model deployed in an enterprise data center, or the enterprise could take the option of a private cloud data center. Somebody asked me, oh, is that why private clouds are back in fashion? Maybe. Option 3, you could have a small model deployed on an autonomous device, like a car or a robot. Or you can have a very small model deployed on a phone. And phones have got AI processors these days. Now, after training, I mentioned that we could use RAG for proprietary or confidential data. We can have context-specific data. As prompting gets bigger and bigger, you could say, here are 6 peer-reviewed papers. Can you please summarize each one in 100 words? But you have to have the size of a prompt that will allow you to copy in all of the context information that you need. And that's context windows, and we're moving to infinite-sized and persistent context windows as future options. You can allow it to think for longer, and that's inference time compute. Now, the growth of electrical power it's unavoidable when you look at it today. Now, this is a forecast, and the thing is, we're already seeing a 3 times increase in the last 12 months. That forecast is already a huge underestimate. And even that forecast used quite old data, so you can imagine why. AI is using huge amounts of electrical power, and companies are caring less how they get that power. If you look at the Google environmental report for 2024, in the past 5 years, they've seen a 48% increase in CO2 emissions. Kind of the wrong direction. They were supposed to be reducing CO2. Microsoft in 2020 made an amazing commitment. They said, but I think they originally said 2030, now they're saying 2050, they're going to remove all of the CO2 that Microsoft has ever put into the atmosphere since it was founded in the mid-70s. Unfortunately, they've increased CO2 emissions by 29% since that commitment was made. Things are going the wrong way. Why don't we take a look at why that's happening? Look at Virginia, which is the biggest data center market in the world. 30% compound annual growth since 2014, 4 gigawatts of power in those data centers today. The forecast is that they will need 11 gigawatts of new data center capacity by 2030 in Northern Virginia alone. That represents 40% of all of Virginia's electricity demands, domestic, industrial, everything today. And so you can imagine this is not a big surprise. If you're trying to build a new data center in Virginia at the moment, you could be waits up to 7 years to connect to the grid, because the grid is just overstretched. So what's needed in Virginia? 10 to 15 gigawatts of firm generation capacity. That's not solar, that's not windmills, that's got to be something like gas-fired power stations. And this is a problem. First of all, the fact that it can take 3 to 4 years of approvals to get a new gas-fired generating station up and running. That's a gigawatt scale gas-fired power station. But the market prices are too low for developers to take a risk and start investing in those new gas-fired stations. And the developers are also saying, well, hang on a second, aren't we supposed to be closing down gas-fired plants? Right? Call me a bluff old traditionalist, but I thought there was this thing called global warming. Well, the trend is now bring your own power to your data centers. Let's see how that worked out for xAI, shall we? So Colossus, which is a very interesting choice of name. There's a film from the 1970s called the Forbin Project, where 2 massive computers are invented, one in the United States and one in the Soviet Union at the time. And of course, they basically start to take over the world. So Colossus in Memphis is xAI, Elon's data center. And the goal was to be the first 100,000 node data center. And also, it's going to scale 200,000 soon, and it's scaling beyond that. 100,000 H100s require 150 megawatts of power. How much power is in that site at the moment? Well, the local power company, because it was basically an Electrolux factory that closed down, it made like refrigerators or something like that, they didn't need that much power. It's only got 8 megawatts going into that power station, into that data center site. So xAI, they pony up with 14 natural gas-powered mobile generators, so not the most efficient way of generating electricity, and that gives them 35 megawatts total, incremental. So then they brought another 4 solar turbines. Oh, thank goodness we're getting some clean energy. Nope. These are gas-powered mobile generators. That's just the name of the company, Solar Turbines. So they're giving you another 64 megawatts. And smog levels in Shelby County have exceeded recommended levels for the past 3 years. Adding all of this natural gas stuff that's spewing carbon dioxide and nitrous oxides, nitric oxides into the atmosphere, not ideal. Now, the electric company has said, we will upgrade the site to 50 megawatts. But the taxpayers have to pay for that, $760,000. They're not happy about that. And xAI has said, well, we'll build a new substation for 150 megawatts, the full amount of power, and it's going to cost us $24 million. Substations do not generate power. They're just connection points. It's just so that you can bring in enough power to the site. Where are you going to get the power? So local pressure groups, including the Southern Environmental Law Center, they're basically saying the grid is overloaded. The asterisk, that's not a direct quote. These are lawyers, right? There's like 2 paragraphs in that quote. But what they're basically saying is the grid in Memphis is already overloaded. Now, the breaking news is Elon's not stopping at 100,000 or 200,000. He wants xAI and Colossus to be 1 million nodes in that location. Now, 1 million GPUs, by the way, was 27% of Nvidia's 2023 shipments. And where is he going to get the 1.5 gigawatts of electrical power to go into that site? So that's one way of planning electrical supply into a data center. Let me give you another example, Singapore. I think I mentioned earlier, I deal with submarine cables. Singapore is one of the most important subsea hubs in the world today. It's in exactly the right position. Between Europe and the Far East, it's a natural crossroads. 26 operational submarine cables, 3 major cable landing stations, and they've got 87 data center facilities using about 1 gigawatt, about just over 1,000 megawatts of electrical power. And over 95% of Singapore's electricity is generated with natural gas. Not ideal. Subsea cables, by the way, they take a tiny fraction of that power. You could almost power a subsea cable with the same amount of power as like 3 or 4 electric kettles. So it's not a great consumer of electrical power. In 2019, Singapore issued a moratorium on new data center builds. They said, we haven't got enough power. You have to stop building data centers. Now they have a neighbor, Malaysia. And Malaysia said, hey, we've got some power, we've got plenty of water, we've got plenty of space. And the city that is just across the Straits of Johor from Singapore, which is Johor Bahru, may become the largest data center market in Southeast Asia in the next 2 years. Now, Malaysia, unfortunately, also doesn't have a great record when it comes to generating electricity. A lot of their electricity comes from coal, but they have committed to increase generation from 27 to 37% of renewable energy by 2030. Now, Singapore, they're trying to recover the momentum because they're thinking, oh, wow, we're losing all of that data center business to Malaysia. But the way they're doing it is to say, oh, you've got to build more efficient data centers. That's not what AI people want to hear. They need gigawatt scale data center electricity supplies. So what can we learn from Singapore? Well, first of all, you need a lot of green energy. Number two, proximity to a hub, in the case of Malaysia, was very, very handy to generate an enormous new revenue stream for them. But number three, don't become complacent. There were press articles back in 2014 that were saying in Singapore, we need to start building some more power stations for all these data centers that are popping up. Now, interestingly, Singapore and Malaysia, they've got a very lively history. Singapore declared independence from Malaysia in 1965. Since then, there have been disputes over water. Singapore gets all of its fresh water, or most of its fresh water, from Malaysia. There have been disputes over islands, port boundaries, and so on. But some good news. The data center opportunity is actually pushing them closer together towards cooperation. And this is a map of a proposed Johor-Singapore Special Economic Zone. And so the island there at the bottom, that's Singapore. And that's where all the subsea cables terminate. And then here we have Johor Bahru. And it's so close. It's less than a kilometer from Malaysia over the bridge, 750 meters distance between the two. It's currently about a 2-hour drive, including a customs post on the Causeway Bridge. And after the agreement, it'll be a 10-minute metro train ride. That's going to be amazing. That's going to be a really fantastic economic cooperation between the two countries. Ireland could be the next Singapore. There's actually lots of candidates for the next Singapore, by the way. But Ireland is a country that has a massive dependence on data centers and hyperscalers. They are a massive tax haven, the third largest tax haven in the world. They also have an enormous per capita GDP generated by all the revenue they get from hyperscalers. However, data centers are currently accounting for 21% of all their electrical consumption in the country. And it's predicted to rise to 30% by 2026. Google wanted to expand their data center in Dublin, and it was rejected by the local council because they said, we don't have enough power. And again, Ireland generates over 50% of its electricity from fossil fuels. How could we power data centers? How do we do this? Well, renewables are fantastic. My garden buildings benefit from solar panels. It's fantastic at that scale. They're not very good for AI data centers. Wind and solar have got major advantages. Low CO2, cheap. Oh my God, are they cheap. They're safe, they're quick to deploy, and there's often local resistance to big solar farms, but not on the scale of resistance you get to a nuclear plant, right? So they have some major advantages. But they don't work very well for a gigawatt scale AI data center, mainly because it's really hard to deploy gigawatt scale solar and wind. The largest plant in the world is not even gigawatt scale. Co-location with the data centers is really challenging because solar and wind take up enormous amounts of land. They're intermittent. So you always need to back up solar and wind with some other kind of reliable power generation. A lot of people choose natural gas. People also talk about a follow the sun approach for data centers. So you just transfer the processing to a data center that's in the sun and the solar panels are generating electricity. But then you're just going to drive up your heating costs or your cooling costs. Now, existing green energy data centers always have to have a backup from a reliable energy source. The three options are nuclear, coal, and natural gas. Well, 2 out of the 3 are CO2 emitting. Nuclear is the only one that doesn't. But they all require a connection to a power grid, as do solar and wind farms, by the way. And we just learned that gigawatt scale grid connections in many locations might involve a multi-year waiting time because our grids are getting very old and very tired. What about batteries? One of the big success stories. So the price of lithium batteries, that graph says fell by 97%, but that graph stops in 2018. I found some more recent data. The actual cost of lithium batteries has fallen by over 99% since the technology was first released commercially. It's an incredible success story. However, the largest combined solar and battery plant in the world, in California, occupies 4,660 acres. That's 3,530 football fields, to use the standard American unit of area, and only generates 864 megawatts of solar PV. It's not even a gigawatt. It's not even half, well, it's about half of what Elon would need for his massively expanded Colossus. That's not a phrase you hear very often. So it also has 3.2 gigawatt hours of battery storage. But that means a gigawatt scale AI data center could only be run for about 3 hours from the largest battery storage facility in the world. A typical largest storage facility in Europe, it would only power it for 40 minutes. It's a plant in Belgium. And they occupy enormous amounts of land. Now, the real concern I have, solar panel waste. It costs between $20 and $30 to recycle a solar panel. It costs $2, less than $2, to send that solar panel to landfill. Where are all the old solar panels going? Landfill, right? Unless you have national laws in place that these things have to be recycled, they ain't going to be recycled. Now, I tried to find a similar statistic for lithium batteries. I know it's low. I know that not many lithium batteries are recycled. We have a big problem in the United Kingdom at the moment. If an electric vehicle is in an accident, most times they have to remove the battery, and we've got a whole bunch of EV batteries stored in a fire-safe facility somewhere in England at the moment because nobody knows what to do with them. Nobody knows if they're dangerous or not. That's insane. Now, what about next generation geothermal? I've got 3 papers, top right there, 3 different papers you can look at. You should always look at more than one paper for any of these topics. The Project Innerspace is an organization that is specifically intended to promote next generation geothermal. The International Energy Agency has often been criticized for not promoting renewable sources and for promoting oil, gas, and nuclear. And I would reckon the Idaho National Laboratory is probably, fairly even-handed. It's also backed by MIT, that report. So conventional geothermal is very successful, but it only provides, it's less than 1% of the world's electricity today because it has to be in the easiest locations. It's places where there are hot springs or volcanoes, geysers, that kind of thing. So US, Iceland, Indonesia, Turkey, Kenya, Italy, all have conventional geothermal. But enhanced geothermal systems basically use fracking techniques to open up a lot more locations. They drill down, they frack the substrata, and they pump down water that gets heated up and then blown out as steam. Enhanced geothermal advantages include potentially low CO2. Why have I got an asterisk on that? Well, when you drill into the earth, occasionally you release CO2 that's been stored underground or has built up underground. Unfortunately, the USA is not a signatory of the Kyoto Treaty, so you're not required to even measure CO2 emission from these kinds of plants. Oh, no, let me just go back. However, the advantages include 24/7, 365 operation. It's good for a data center. Small footprint, also good for a data center. Very interestingly, the skill sets match the oil and gas industry. So as you're closing down your oil and gas industry, you can take all those highly skilled people and transfer them to this renewable, this clean energy industry. The disadvantages, potential emissions. It's not just the CO2. When you drill into the earth, all sorts of stuff comes up. Hydrogen sulfide, there's all sorts of noxious gases. Those are regulated. CO2 is not regulated in the US, but the other gases are. You have potential waste production because slurries come up from the rock. Potential for seismic disturbances because you've been fracking. But most designs, the biggest disadvantage, they're kind of megawatt scale or tens of megawatt scale. They also potentially need a lot of water. But these new EGS systems are also unproven. However, the Idaho National Lab, they basically say, look, there's the potential to create 100 gigawatts of new geothermal generating capacity within 50 years. And it will only cost between $600 and $900 million. Now, that might sound like a lot of money, but let me introduce you to nuclear power. Now, nuclear power is one of the most successful clean energy sources in the world. Incredibly safe, incredibly clean, and incredibly reliable. However, Vogtle 3 and 4, right here in Georgia, these are the first new nuclear plants that the US has been built in decades. 4.5 gigawatt power output, sounds good. However, the original time frame of 2017 for coming online slipped to 2024. That's not great. And the costs have risen from $14 billion to $37 billion. That's 2.6 times over budget. Don't feel bad. In the United Kingdom, Hinkley Point C, also the first nuclear plant built in the United Kingdom for many decades. 3.2 gigawatt output. Original time frame of 2025 has now slipped to probably 2031. And the costs have risen by a factor of 4. Now, wait a minute. Okay, so the US and the UK, they don't generate most of their power from nuclear. Let's choose a country that generates 75% of its electricity from nuclear. France. The Flamanville 3 in Normandy, 1.65 gigawatts power output. Original time frame, 2012, slipped to 2024. It slipped by 12 years. And the budget is 6 times over budget. Okay? Now, there's another interesting thing here. All 3 of these are examples of pressurized water reactors. Fun fact, where do all of these reactors, and in fact every other pressurized water reactor in the world, where do they get its fuel from? From Russia with love. It's the TVEL company, it's a subsidiary of Rosatom. All of the fuel comes from Russia. Now, the nuclear part's really not the problem because no mega project that's been built recently has come in on time and on budget, right? You look at the Three Gorges Dam, 4 times over budget. You look at the Venice flood defenses, 4.7 times over budget. You look at, in Boston, USA, the Big Dig, 8.5 times over budget. These mega projects, they always overrun. And it turns out we were never that good at project estimates. The Sydney Opera House was 14.6 times over budget. The Sagrada Familia in Spain, it was started in 1883. It's still not finished, and nobody knows how much it's cost. And we don't even need to have mega projects on Earth to overrun. The International Space Station has overrun by a factor of 10 on its budget, right? We're not very good at building large-scale projects. So it will not surprise you to learn that the hyperscalers' plans for bring your own power include smaller nuclear reactors, small modular reactors, as they call them. But they have all sorts of other plans as well. So let me just give you a summary. Amazon, you may have seen, purchased a 900 megawatt data center next to the Susquehanna nuclear plant. Fantastic idea. They'll be up and running very, very quickly. Longer term, they have plans for SMRs, small modular reactors, in 3 US locations. And they have an anchor investment in the X-Energy company, which is building small modular reactors. Google has geothermal investments with Fervo Energy. This is the enhanced geothermal I was mentioning. And in October, they announced an agreement with Kairos Power for small modular reactors. Microsoft, they signed an agreement to reactivate the reactor at 3 Mile Island. Fun fact, the 1979 accident at 3 Mile Island, which was a different reactor, killed nobody. The amount of radiation released into the environment was about the same as if you take a flight from Boston to San Francisco. I mean, it was a negligible amount of radiation release. And in fact, the nuclear industry is the only industry that's regulated for its radiation output. If you live downwind from a coal-fired power station, you've been exposed to way more radiation than a nuclear plant would ever be allowed to release. Okay, so they've also got clean energy credits. Yeah, they're not really very useful. It's a bit like when they say, would you like to plant a tree to offset your flight to Atlanta? Yeah. You know, the same tree is actually, they plant the same tree for like 15 people. And they also assume that the tree is already 15 years old in terms of the amount of CO2 it's absorbing. So these clean energy credits are not worth much. But they have a small modular reactor deal and a clean energy deal with Ontario Power in Canada. They also have a nuclear fusion deal with Helion. Nuclear fusion. That's very exciting technology. It's probably decades away. Oracle are talking about a 130,000 node cluster, and they've talked about the intention to build small modular reactor powered data centers. Meta have plans to build a data center near a nuclear facility like Amazon and Microsoft, but it was blocked because of an environmental study found it was going to endanger a rare species of bee. Now, Meta is going to have to rethink where they build that data center, but they're probably still wanting the same power from that nuclear facility. But they also signed an agreement with Sage Geosystems for a next generation geothermal technology. So, small modular reactors, how's that going as a technology? So you may be aware that when you design a reactor, you have to go through certain stages. And the ideal stage to be at is the operational stage. How many operational SMRs are there in the world? 2. One in China, which is actually a high-temperature gas-cooled reactor, and one in Russia, which is on a ship. This is really cool. It's a mobile nuclear reactor that is sailed into places that need electrical power. And it's based on their nuclear powered icebreaker reactor technology. So very, very cool technology. They also, actually, there's another one, a pressurized water reactor. So under construction, we have China building a standard pressurized water reactor design, but my favorite kind of small modular reactor, which is a thorium-powered reactor. At the beer and gear later, if anyone wants to talk for about half an hour on thorium with me, I would be happy to talk about it. It is the coolest nuclear fuel of all. So very excited about that project. In Russia, there's a light water reactor, a lead cooled, that's a fast spectrum reactor that can burn nuclear waste, which is very interesting. In Argentina, again, that's a slightly unfortunate project because it's one of these projects that's just overrunning and over budget. And then 2 pressurized water reactors in Russia. So they're all under construction. Licensed, which means you've finished your design, you've taken it to the licensing authority, and they said, yep, that's okay, you can go ahead and build them now. So licensed in at least one country. We have Hyundai in South Korea have a pressurized water reactor licensed, and NuScale in the United States have a pressurized water reactor design licensed. They tried to build it, but they didn't build it for a hyperscaler. They built it for a local community, and they ran out of money. Why the hyperscalers are not queuing up at NuScale's door, I have no idea, because they have a finalized design that's ready to go, but they just need the funding. seeking a license, which means I've finished my design and now I'd like to license it, please. We have in the United Kingdom, Rolls-Royce, a pressurized water reactor design, and Holtec in the United States. In design, which means, yeah, we're still kind of thinking about it, lots of different reactors, including all the companies I mentioned that the hyperscalers are investing in. X-Energy and Kairos. Copenhagen Atomics, by the way, are also developing thorium technology, my favorite nuclear fuel. Really need to get out more. It could be 10 years or more between the in-design stage and the operational stage for these SMRs. So, what is the status of these SMRs? If you'd like to read a report about it, the Institute for Energy Economics and Financial Analysis says, oh, they're still too expensive, they're too slow and risky. So their key findings are that, yeah, they're expensive and they're risky. They're not really any less expensive than building a big nuclear reactor. Now, I would like to give my comment on the conclusions to this report. The conclusions to this report are looking at the general energy market. And the energy transition for the rest of the world is not the same problem as the hyperscalers are facing with gigawatt scale power AI data centers. I think cash-rich hyperscalers could literally push SMRs through to completion. And once these things are running and we've got them popping off the production lines, they're going to be quick, cheap to build for all of us. And this is a much more interesting technology. So, by all means, read that report, glance through the conclusions if you don't want to read the whole thing, but think about the problem the hyperscalers are actually facing. So, there are 3 steps to nuclear-powered data centers. Number 1, grab any spare capacity you can on an existing nuclear facility before your competitors do. That's what Microsoft and Amazon are doing. It's what Meta is trying to do. Extend the life of nuclear plants that were scheduled to close. Reports, links to reports here and maps of nuclear plants that were scheduled to close. In 2022, the US Department of Energy warned that 25% of US nuclear plants were threatened with risk of economic closure. That's insane. Step in and stop that happening. It's happened in a couple of different places already, fortunately. Number 2, restart any mothballed nuclear facilities. There's what would you call it? It's a process called SafeStore in the United States. It's about how you mothball a nuclear facility. And in the earliest stages of SafeStore, you can restart them. So they think they're going to be able to restart the Palisades plant in Michigan. That may be the first to restart in the USA. Then, of course, 3 Mile Island for Microsoft. Nobody knows yet whether they can really be restarted, but we think they can. In Germany, they shut down 11 nuclear plants prematurely. These were probably the safest nuclear plants in the world. They're German nuclear plants run by German engineers. It doesn't get any better than that. 26 gigawatts of clean energy lost. Now, the CFO of E.ON, Nadia Jacobi, says, well, there's no economically sensible way of bringing these plants back. And the reason for this is that 3 Mile Island was mothballed for economic reasons in this SafeStore architecture with the option to restart. But Germany's reactors were shut down for political reasons. There was no intention to restart them. Step 3, build new large-scale nuclear plants, if you remember how to do it. Now, there's a link there to US goals for their nuclear plants, and these are very aggressive. 35 gigawatts of new nuclear power by 2035. 15 gigawatts of new nuclear power per year after that. That's a really aggressive, that's like a moonshot goal, basically. Develop new kinds of nuclear reactors like SMRs. Very long-term hope is that somebody figures out nuclear fusion. There's a Chinese research group that has recently broken the record for maintaining nuclear fusion. 1,066 seconds. That's the world record at the moment. Now, I think nuclear energy has some real problems, but it also has a few non-problems that people like to talk about. For example, safety. Well, think about it. There's been 3 major nuclear disasters in the history of nuclear power. 1979 with 3 Mile Island, 1986 Chernobyl, and 2011 Fukushima. The only one of the 3 that produced any fatalities was Chernobyl. A badly designed reactor in a very poorly maintained state, which you then perform a safety test on against a number of recommendations from the engineers running the plant. And you're surprised when it goes bang. Oh, and by the way, you never built a containment building around it like every single Western reactor has. So, it costs $2 billion to build a containment building after it's gone all radioactive. Now, horrible tragedy, 88 people died. 88 people died. When Germany decided to close down its nuclear reactors, it had to maintain coal-fired power stations beyond its original scope, beyond its original plan. It's estimated that 1,100 additional deaths occur every year in Germany because of poorer air quality, because of burning coal. We need to get a grip on what is safe and what isn't. Bombs, proliferation, right? Every design for a modern nuclear reactor goes through the process of being proliferation resistant. And we just have to leave it at that because it's very complicated. Waste. I'll say something very controversial. Nuclear waste is a choice. It's not an inevitability. We were always supposed to reprocess nuclear fuel rods from nuclear power stations. Turns out that it's more expensive to do that than just mining new uranium. Only France reprocesses 95% of its nuclear fuel rods, and it makes new nuclear fuel out of them. We could all do that. Levelized cost of energy, the cost of nuclear power. Everyone says it's really expensive, but they're comparing it with solar and wind on their own. They're not comparing them with solar and wind with enough batteries to be as reliable as nuclear. That changes the perspective dramatically. What are the real problems? They cost a fortune. The capital costs are insane. And the time to deploy is just crazy because of regulations. And of course, the time to deploy affects your capital cost because you're paying more interest on the loans that you took out. Public fear also increases the time to deploy because you have all these action groups trying to stop you building them. And then forgotten skills, right? China and Russia have entire generations of new nuclear engineers. At one time, the US Navy was the biggest source of nuclear engineers for the US domestic nuclear engineering business. Probably still is. We need to remember how to build these things because that compounds all of those other problems. And let's not forget the consumption of water by data centers. So there's a number of different ways of measuring the water consumption, Scope 1 water, Scope 2 water. I've given a link to the report that explains these, but let's just take a few simple examples. The global consumption of water by the AI data center market is estimated to be about the same as Denmark, the entire country of Denmark. It's about half of the United Kingdom. Producing one GPU chip requires 8.3 tons of ultra-pure water. 100,000 GPUs in the Colossus data center need 830,000 tons of ultra-pure water. Training the model, if it's done in Iowa, for some reason, it's only 4.8 million tons of water. If it's trained in Washington, 15 million tons. Using the model, inference, about half a liter per 50 questions. 10 million questions a day, so that's 36,500 tons of water per year for inference. So I'm going to move to a different topic. Will AI and robots take my job? And also, a lot of you here will have kids, you'll have perhaps younger siblings, you'll have nieces, nephews. What kind of advice would you give them if they come along and say, I'm thinking of getting into this, that, and the other. What should I do to avoid AI taking my job? Now, in 1964, that great philosopher, the Twilight Zone, predicted what's going to happen. In an episode called The Brain Center at Whipple's, Series 5, Episode 33 of The Twilight Zone, a heartless CEO, Wallace V. Whipple, he automates his family-owned factory, lays off 61,000 of his workers. Now, that's very realistic. What's a lot less realistic in this episode, it really lets the episode down, to be honest, is the fact that some of his executives disagree on moral grounds. Right? That's not going to happen today. And also, his workers completely fail to see the opportunities presented to them for more leisure time. Right? They're very annoyed at this. But it's a great episode to watch. It really kind of, brings it home. Now, here we see the top 65 jobs that are supposed to be safest from AI and robot automation. So this is from the US Career Institute. And, spoiler alert, 36 out of 65 jobs listed are in the healthcare industry. There's a link to the full report there. There are many other similar reports. Like I say, you should never just read one report. Lots of different reports, all linked. Each of these images is a link to its report. The OECD link actually takes you into a lot of detailed reports that go into specific industries. So let's see a success story for OpenAI's technology. So this is from OpenAI, also from Wikipedia. There's a Swedish company called Klarna. Now, Klarna, they're like a Swedish financial services company. When you make online purchases, even from eBay, one of the options is to pay through Klarna, and they give you a kind of buy now, pay later, credit kind of thing. So their 2023 revenues, $2.12 billion. They, 5,000 employees listed on the Wikipedia website. They've had a really roller coaster ride because in 2021, they were Europe's most valuable private tech company, $45.6 billion. But 1 year later, the valuation had dropped to $6.7 billion because they failed on a round of financing. I mean, you know how this thing goes. February 2024, they announced that 10% of their workforce has been replaced by AI agents. These are customer service agents, basically. And they said the agents are doing the work of 700 people, and all sorts of advantages given in the case study. Now, the big thing was that they were credited with driving $40 million of profit improvements for Klarna. Big success story. Even in Sweden, none of that $40 million goes to any of the 700 people laid off, right? Even in Sweden. And if you think about what's going to happen as people get laid off because of AI, it's not like now there are other jobs that they can go to because all of those jobs are being replaced by AI. Software developers. Zuckerberg, of course, he said that AI will be doing the work of mid-level software engineers this year. And, he's not the only person making statements like this. There's an order of replacement that seems to be around in the software industry. The first kinds of programmers out the door are going to be people who work on algorithms and data structures. And the reason is that they can be broken down into small chunks. AI is very good at dealing with those kinds of software problems. Programmers on JavaScript libraries. If you've ever programmed in JavaScript, you don't do any real programming, you're just administering library calls, right? React.js, it's basically a complete library of simple calls to make programs. The safest programmers are the freelancers because they are the people who need to be the most flexible and creative. Every job they do is different, so they will be the safest programmers. Gartner has this iceberg diagram that they show of basically the magic quadrant for AI code assistance and all of the advantages of these technologies. And the biggest productivity gains are going to come with code assistance, where the humans and AI work together for the moment. Because there are 3 stages in this kind of replacement. Now, this is for surgeons. Far be it from me to suggest that network engineers should be an example of this. But think about it for surgeons. Step one, human brains, human hands. Step two, which is where we are today, human brains, robot hands. And then the goal, AI brains, robot hands. Because 15 years to train a surgeon, right? Whereas we can churn out thousands of these robot AI-driven surgeons. So I'll give you a couple of quick predictions before I finish. There's a lot of predictions, so let's look for some patterns. IBM, Microsoft, you could argue that agents have already happened. If you look at Expo, which is a penetration testing company that uses AI, Agentforce, part of Salesforce, and Project Astra at Google is a big example of agentic AI. MIT's technology review's got a different set of predictions, more imaginative in many ways, generative virtual playgrounds, where you can go into an AI world, and instead of it being predefined, it's generated on the fly. Very interesting. Now, most people agree that AI agents will be hot in 2025. So remember the example I gave of compound AI. So, the RAG system. Now, instead of me asking about my how many days off in the time off database, if I asked it, well, what's the weather going to be like in my vacation destination? Well, the time off database isn't going to be able to tell it that. However, RAG is like phone a friend. If we got a question on motor racing, we wouldn't call an expert on classical music, right? You'd want to choose the correct friend to phone. And that's what agentic AI basically does. What you do, you have the large language model, which receives a query and evaluates it, and it decides which of the various databases and tools that it needs to refer to. An example of a tool, by the way, could be a calculator, because AI is really bad at arithmetic. And it will check with the large language model which is the best tool to use. So, the LLM says, oh, database C is the best one to choose here, and it incorporates that data into a prompt and evaluates it. So I'm going to try and summarize here, and I do need to have a disclaimer. The following slide is my personal opinion, right? It's not the opinion of any company I might work for or anyone I met at the conference. It's my opinion. So how do I summarize 90 minutes or 80 minutes of presentation? We've got this once-in-a-lifetime AI opportunity. But that means we need better AI. How do you get better AI? Oh, well, you can think of it in absolute terms or in relative terms. But however you think about it, it needs more processing power. More processing power implies more electrical power. And those pesky corporate sustainability goals that we thought were a really good idea 10 years ago are turning around and sort of biting us. Renewables are not a great fit for AI data centers. Over 80% of solar panels are made in China, right? All of the nuclear fuel for our pressurized water reactors is made in Russia. And by the way, the HALO fuel that's being planned for Bill Gates's Natrium reactor, also made in Russia. And so they say, oh no, we were only kidding with those corporate sustainability goals, just carry on burning coal. But there are consequences when you do that. Unfortunately, a few people have answers to that, right? Some of them will be going to Mars, because it's not going to be us. It's like the 0.0001% might get a ticket to Mars. But no, it's okay. We will use nuclear power. Seems like a great option. But we've forgotten how to build nuclear stuff. Well, not everybody has forgotten. There are people who still remember how to build nuclear power plants. China is rolling out 130 nuclear plants in the next 10 or 15 years. Oh, and by the way, are they overrunning budget? Are they taking too long now? Yeah. But once they've rolled out the 10th or 13th power plant, they'll have figured out how to roll them out properly. And the prices come down, they get on time, right? Every time we build a nuclear plant, it's a completely different design, and we're starting from scratch. Anyway, let's look on the bright side. AI provides massive productivity boosts. Whoop, whoop. But we all lose our jobs. But then the hyperscalers suddenly think, hang on a second, who will buy all of our stuff? Right? If everyone loses their jobs, who buys all the stuff that we've got this AI for in the first place? Now, there are people who have answers to this, right? Proudhon, you know, if your history of political stuff, Proudhon was a utopian socialist, right? And no, he wasn't a Marxist. Marx hated him. So he wasn't a communist. He was he had ideas about how you could have this utopian socialism. Yeah, I mean, people have talked about universal basic income as being a replacement for the revenue, but who knows what's going to happen? It's going to be an interesting time, and I hope that's been an interesting 80 minutes or so. Thank you very much.
Well, thank you, Jeff. That was a fantastic presentation. I really enjoyed it. So now, do we have any questions in the room?
You are allowed to ask me questions during beer as well.
Going once.
Jeff, I have a question.
Yep.
So I don't understand how, especially like a private company is going to be able to build nuclear reactors, whether they're small modular or not, given the lack of density of engineering prowess, especially in the United States, and the lack of understanding about how it works. How is it going to work politically?
So those are two very different questions. So the question was, how does a private company build a nuclear power plant, whether it's a small modular reactor or a large-scale reactor? That's a massive question, because first of all, it's the technology question. And the simple answer, we've just got to get better at doing it. I think one of the problems now, if you look at the United States, is being driven by free market economics. So instead of finding one good design and putting all your effort behind it, you've got like 20 designs. And they're all just fighting for venture capital funding. But the problem that NuScale found, funding runs out. If you don't have somebody with extremely deep pockets, it has to be a hyperscaler, honestly, extremely deep pockets to fund this kind of capability. And by the way, imagine the hyperscalers benefit when you actually get it working and you can churn them out like a production line. That's going to be amazing. So that's answering the first part, the sort of technology aspect. But then you asked about the political aspect. Now that's going to be so difficult. Well, Biden actually introduced huge plans for the nuclear scale-out. The link that I gave to the US plans for nuclear power rollout, that was a Biden initiative. I don't know whether Trump's going to carry that on, but I hope so, because that kind of moonshot project has to have political support behind it. But at the end of the day, you cannot make it a party political thing. It's too important for that.
Do you think, so Amazon's going to build a data center region?
Yep.
Somewhere.
Yep.
And they want to put a nuclear reactor in. Do you think the local population is going to allow that to happen? I'm not asking this rhetorically. Do you think, how's it going to play out?
I think it depends which state you're talking about. There are a lot of places that have or did have nuclear power plants, and the local communities remember with fondness the highly paid jobs at those nuclear power plants. If you put it in California, right, you're going to get every environmentalist objecting to it because they think nuclear is not green. Remember, the founder of Greenpeace actually left the organization because he said you're becoming an anti-nuclear organization, not an environmental organization. So Greenpeace sort of lost the plot decades ago. But people have to realize that nuclear is clean and it's safe. But how do you convince people of that? I don't know.
So essentially it'll turn into a competitive scenario like the Singapore.
Could do. It could do. And certainly phase one, everyone's going to race for whatever nuclear power is available. So, yeah.
Renison, Cisco. One question about the open source models, right? So Zuckerberg started the Meta Llama, right? And now we have a DeepSeek and all of that. So where do you see, not your employer's opinion, your opinion, where do you see this open source models goes, and where do you see maybe 5 years down the line, and what are some of the new challenges they're going to face?
I'd see a lot of parallels to the original Linux open source market, because when Linux first went open source, everyone says, well, how are you going to make money out of that? And then Red Hat showed everyone how you make money out of that. It's not about the fact that the software is free. Enterprises don't buy just open source software. They buy solutions. They want a complete service package, a support package. And I think the same thing is true with AI models. You're going to get highly specialized models. With the reduced training requirements that DeepSeek showed us, with the inference time compute, instead of very extensive training, you could have specialized AI models where all of the stuff that was in RAG, those external databases, could be brought inside a proprietary trained large language model. That would be an interesting option. And you take an open source large language model and you effectively retrain it. They've got ways now, so they call it distillation, if you look at the DeepSeek. So you distill another model out of your open source model that's now been trained on the proprietary data that you have. But it's your model. You don't put it out to everybody. Now it's a proprietary model. So I think that's one of the options. But I think the more generic way of looking at it is in exactly the same way that Red Hat treated Linux. And you build your money on creating a solution and wrapping it in a services wrapper.
Maybe a follow-up, I think. That there's a bill being circulated by Senator Hall, right? I think Senator from Missouri, and it's going to penalize the use of models from China and export to China, right? And I think open source models going to be included as part of that exercise. And I think the language is very harsh, very, very vague at the moment. So I'm not sure if you have any opinions on that one.
Yeah, I mean, honestly, I think it's almost pointless having these political discussions, especially when you get this polarization between, the USA and China. Same thing with Europe and China having problems. It's crazy. We need to get over it. We need to find a way of unlocking that whole situation, I think, and just resolving it. Don't keep on punishing each other. That's crazy.
Yeah. Thank you.
Any more questions? Okay, with that, Jeff, thank you for your presentation, and we appreciate your contribution here.
Thank you.